Hello everyone, welcome to the POSTECH Math Colloquium. So today it is our honor to have Professor Minsung, who was a PhD in University of Maryland, and he did some postdoc at many countries in Europe, which is Italy, Sweden, and Poland, and Sweden. And now he is okay. So let me say. He has been postdoc of Nikola Copernicus University in Poland and then Scuola so in Italy and KTH Royal Institute of Technology in Sweden. And now he's an assistant professor in our department at Paul University. And so he's going to give us a talk on rapid mixing for random works on new manifolds. Let's welcome him to give us talk.
Thank you for attending the talk. So actually, this talk will be about dynamical systems, but actually it contains several things. So mixing is for dynamical system, but random walk is for probability. And the manifold is about some Lie groups. So in this talk, I want to introduce how these things interact each other in the sense of dynamical systems. So I think that most of you are not familiar with the topics. So please ask me any question in the middle of the presentation. So I want to introduce what is dynamical system. So in dynamical system, we have a complex space and we consider a map or flow. So I assume you know the definition of flow, but just in case you don't know, then it just satisfies the group property. So flow is just written as a one parameter family. And if you fix the time t is equal to 1, for instance, then you can obtain a map. So I will write capital T as a time 1 map of the flow. So in dynamical system, we are interested in the trajectory. So in here, I wrote the T is positive, I mean greater or equal to 0, but it can be also T is in R. It doesn't have to be positive. So if, just roughly speaking, if you have any point X, then we are interested in how the point moves around in a space. But actually, when time tends to infinity, we want to know how it behaves. So in that is one of the objects in dynamical system. We want to know what will be asymptotic behavior. But for the single orbit, it is very difficult to know because for every point, you may have an orbit, but it will be difficult to know because each of the points may have a different behavior. So actually, that is kind of known as a butterfly effect. But yeah, so in dynamical system, we like to say almost every point, it has some common behavior. So so that is one idea. And if you consider M as a complex space, it's not always, but mostly we have a measure. So this is an invariant probability measure because we want to know in what sense the orbit behaves. I mean, what will be the typical behavior of the orbits. So roughly speaking, dynamical system can be divided into three: hyperbolic, parabolic, and elliptic. So if you just think like a matrix, it will be the analysis of the eigenvalue. So in the parabolic, actually, I'm interested in some parabolic case. So parabolic means if you have if your matrix can be diagonalizable, then it has eigenvalue 1, and also it has an off diagonal, but eigenvalue is 1. So one of the characteristic for parabolic system is it has a polynomial divergence. So if you see in the picture, we have two different points, x and y. But if we consider flow trajectory, then at the same time of t, then the difference of 2 points grow in the polynomial way. So this is the meaning of differential of the flow is a big O. So hyperbolic system means the difference of 2 points grows in exponential way. And the elliptic means it diverges in subpolynomial. So it will grow like logarithmic. So in the hyperbolic case, actually we always have a very nice property, because if you consider a tangent space or tangent bundle of the space, then you always have a natural splitting. So you have a stable or unstable. So again, if you think of matrix, then your eigenvalue can be larger than 1 or smaller than 1. And you have also invariant subspace. But in parabolic case, we don't have such invariant subspace. That is one bad part or the difficult part. For the elliptic case, the speed of divergence is too slow. And you can, so there are not many examples in elliptic system. So it is kind of well known in some sense. So parabolic system is also known for the zero entropy system. So in the sense of the divergence of the distance, we call it as a zero entropy system. And this is less known. So before introducing mixing, we can see some ergodicity. So ergodicity means we talk on a space M and with a measure, and we have a flow. And A is an invariant set. So if you take the measure of the flow, then it is still the same because it's an invariant. But ergodicity means its measure should be either 0 or 1. So it's like 0, 1 low in probability. So let's see some easy example. So this is a circle rotation. So if you consider circle rotation on the 0, 1, then, 1 is identified as a 0. And we can consider its orbit trajectory in the following way. And we will have n alpha. So if alpha is rational, then after some rational time, and after some natural number, and after some iteration, it will come back to 0. Because we can write alpha as a p over q, like this way. But if it is irrational, then it never comes back to the 0. So in this case, we call orbit distance. And so if you see in the rational case, then you can choose some neighborhood of 0. And then if you travel around, then you can find a invariant set. But this measure is not equal to 0 or 1. So when alpha is rational, this is not ergodic. But if alpha is irrational, this is ergodic, because we cannot take such interval. The orbit is dense, so eventually it will be the whole space. So another example is a rational billiard. So in the two-dimensional, we can also consider the similar setting. And we can see the orbit trajectories are either the periodic, that is a blue one, and the orange one is orbit is actually dense. So in this case, is also the example of the ergodic system.
Just a small question. So what is the definition of the invariant set over here? This invariant set.
What is invariant set?
Yes. That means invariant.
Yes. It means just in the sense of the measure. The measure is the, the set itself is not invariant. If you take the measure, then they are the same.
Is there two different measures? So what
No, we consider one single measure in the system.
Yeah.
So in this case, if you choose this one as an A, and this one will be TA, but these two are not the same. The measures are preserved in the sense of the measure that. So you can just think like, if you take the measure, then this is the same. But A and TA are not the same. Yes, or
Okay, I see.
I think, but in this case, I think you mean invariant set. I think that means in this case it will be should be invariant set. I think this
It's
is
not my understanding.
yeah because the whole set is not only single one. So now this is a definition of mixing. Actually, mixing is a stronger property than ergodicity. So given measure, it satisfies mixing means if you have a measure and have some intersection with the orbit of flow or the map, and then it can be asymptotically, it will be getting close to the product of two measures. So actually in probability, we saw without limit and without flow, we call this kind of system is independent. So actually in dynamical system, we don't have any independence in the random variable. But if you have a mixing in asymptotical sense, we can have something like it, the independence. So in the equivalent way, so for the mixing part, so here the bracket is for the L2, and actually this function is called the correlation. The correlation converges to the product of the integral. So precisely the correlation, yeah.
So X is M, right?
X is n.
And X is N.
X is m, yes. Yeah, X is n, yes. So if you consider the map instead of law, then we can write a correlation in the following way. But actually correlation means the difference of two quantities. So if the system is mixing, then the correlation tends to 0. So you can view a function as a random variable in the sense of probability, but if each fn is composition with t are not independent. So mixing means f composed with t to the n is asymptotically independent. So actually in dynamical system, we are interested in the speed of decay. So now I will fix the map. In the case of map, and this map is exponential mixing with respect to measure. So given observable f and g, then the correlation function is exponentially fast. So here the lambda is between 0 and 1. And also here you can see I didn't specify which observable. This is only b, but b should be some function space. So to check exponential mixing, there are two important things. So either the first thing is your map should be nice. I mean, nice means at least it should have some hyperbolicity to guarantee some exponential mixing. The second part is you need to have some regularity. So I will see some example when the exponential mixing fails, even though the map is very nice. So next one is a rapid mixing. A map T is a rapid mixing. So it's the same statement, but the difference is the speed of decay. So your correlation function can be bounded by n to the minus s. So in this case, the correlation decays as a sub-exponential. So it can be, the bound is a super polynomially. So you can choose any s, and you can also choose any r. I mean, the r is for the regularity. And also in particular, we will only consider CR space in this case. So this is the main difference of exponential mixing and rapid mixing.
Oh, sorry, what is B in this?
So I didn't specify. It should be a function space or Banach space. Yeah.
Oh, sorry, can I look at previous slides when you define mixing?
Because here I only wrote any bounded function.
Oh, okay.
So
I see.
yeah, in general, it should be function space should be smaller.
I see. Okay. And why does it call the mixing? Why does it call the mixing?
So why does it call mixing? Because you have a system So if you have a system, you can choose a set A and also set B. But if you iterate some map,
No, that's not.
well, I think for the student, I will. When your set, the after iteration of T, then your set will be very, how to say, it's very distributed in whole space. And then your B is still the same. And then you can choose actually any B inside of, but its density is more or less the same. I mean, it's very equidistributed. That is the meaning of mixing. So for example, if you consider any rotation, if you have a rotation, then it just moved to different place, like this way. So we don't have such, how to say, your set is not well distributed. So the circle rotation is not mixing, but it is mere body. So that is a kind of physical interpretation. So the next example is a f of x. Actually, I think it should be t of x. It's not f of x. T of x is equal to 2x. So this is called expanding map, and expanding map is very nice and it's also hyperbolic. So as you see in the picture, the 2x stretches your set. So this is actually this is a right example for explaining the mixing. So to compare the correlation term, we have a f composed with t. So here I wrote the use of t as a composition. So to recalculate the correlation part, here I just wrote L as a dual operator. But in this case, I didn't define the function space. L is just dual operator of the Koopman. Koopman operator is just composition. So we call L as a transpose operator. And in this case, we can write explicit form. So L of G can be written in the following way. So now if we can check the norm of L is less than 1, then we are good because this is contraction. So if you come back to correlation part, just imagine your integral is equal to 0. And if you have a correlation, then you can apply the dual operator. And if the bound is less than 1, then everything is good. Then it's the exponential mixing. But in this case, actually you can see the L1 is not good space. If you choose L1 as a function space, then you cannot verify exponential mixing, even though your dynamical system is very nice. So the way is to choose a smaller Banach space. So here we can choose W11, which means the first derivative is in L1. So if you choose some smaller Banach space, then you can actually prove the exponential mixing for this kind of map. But this is one of the examples for uniform expanding map. So today, actually, I will talk about rapid mixing, but so actually, he is a Dolgopian, Dmitry Dolgopian, and he was recently chosen as a ICM plenary speaker. And he made a great contributions in connecting probability and dynamical system. So his expertise is improving the rapid mixing and exponential mixing. So in general, as we saw, to prove the contraction of operator is not easy. So actually he invented his own way to prove some exponential mixing, not just using the norm of the operator. So this is called the Dolgopius inequality. And actually Dolgopius inequality was widely used not only in dynamical systems, also in some area of PDE, as long as I know. So in the hyperbolic flow, actually I need to explain what is hyperbolic flow. So we have a flow. So I start from x, and I will start at t of x. And then this is our space M, and this is our tangent space. So in this case, we can split like, so ES means this is stable. You can just think like eigenvalue less than 1, and this part is unstable, and EC. So EC is just flow direction. This is just a flow direction. This is just one-dimensional. So you can see the e to the u, you can just think like y is equal to 2x. It behaves like y is equal to 2x. And this part you can think like it contracts by f. So in such a system, so for every point, they keep the invariant subspace in the tangent space, and they also keep the hyperbolicity except the flow direction. That is the meaning of anosode flow. And Chernow actually firstly proved exponential mixing for such flow. And actually Dolgopia used his own method analytic method to prove exponential mixing for some general anosode flows. So that was actually done in late 90s. And after that, he also began to apply his method to prove some rapid mixing. So if you have only hyperbolicity, then this is fine. We can just apply Dolgopia's idea. But if you have some mixed system, then it becomes more complicated. So let's see. So we saw T of x is equal to 2x. This is uniform hyperbolic, and this is also exponential mixing if you don't choose function spaces in L1. But now I want to consider some skew product. So what does it mean? So we have a T to x, but now I want to consider x cross y and x cross y. So in this case, it is exponential mixing. But now I care about some product. I mean, this is some skew product. So in the sense of y, I mean, this is a fiber, but in the fiber, we will have some non-hyperbolic system. So for example, let's say I will have some elliptic system. Then system is a hyperbolic cross elliptic, but this is not just cross. I mean, this should be some skew product. So in this case, we can ask the system T tilde is still exponential mixing, or this is rapid mixing, and so on. That was the beginning of the question. So this is the Dolgopia's question. And then actually we can also choose y as some other space. So actually, especially he considered the compact group extension of hyperbolic system. So let's see what is the compact group extension. So now we assume G is a group, and actually G is a Lie group, and Y is a G space. So if you have a group, then it acts on Y. So it has a group action. And we consider a skew product that I just explained, and T tilde is defined by some skew way. So in here you can see in the fiber sense, it depends on the omega. So it also depends on the point on the base. And the tau is chosen as x to the g. So we can see also some easy example. So I will choose x as a sigma plus m. So it means we can consider m different words. So yeah, I will just want to m. And our t is x to x. But this is given by t of omega is omega 1, omega prime. So here the omega is a word. I think should be m. This should be m. So this is called the word. And then we can choose the omega 0 and omega k and so on. So you can just think like 1, 2, 1, 4, 3, and so on. But for each choice, I want to assign a probability. So I will assign P1, and this is Pn. Because for each word, you can choose a letter, but I can choose any between 1 to n. So the sum of Pi is equal to 1. Then what will be the image? P of omega, it should be omega prime. But I will write this one as a shift map. So I think if you take functional analysis, you also solve the shift map. But W1, W2, and WK, and so on. So I will forget about the first guy. So it starts with just omega 1. So in this case, now G is a Lie group, and we care about some group action. So what will be the tau omega of what is this? Tau omega of y. So our omega is W0 to WK and so on. But in here, I will choose omega 0. And I will index some omega 0. But this element inside of G. But this x on y. But y is a G space. This is still inside of y. So this definition is actually good. Because if you iterate this map of y, and then you can see on the base level, you have just n shift. But in the fiber level, you will have a product. And write a map in the following way. But now we can see in the base, we assign a probability from P1 to Pn. So this part is just a product, but actually this is a random product. So if you think your y as a y is equal to torus, then your G will be just rotation. But we already saw the rotation is not ergodic, right? It's not even, rotation is ergodic, but it's not mixing. So in the base, we have exponential mixing, but on the fiber sense, this is elliptic. We only have a rotation. So this is quite natural to ask, still our such kind of mixed system enjoys any mixing or fast mixing system. So yeah, in the Dolgopian, in his 2002 work, he considered when the group is compact group, and actually he also considered G is a semi-simple group, and when X and T on the base is hyperbolic, then he proved T tilde is a rapid mixing. So this is what actually I just explained. If you have a group, and F is G1 to Gm, because on the base case, in the base, I can choose a different letter from 1 to m. And then it induces random walk on the fiber. And if a system T tilde satisfies rapid mixing, then it satisfies central limit theorem. So in the fiber, we have xn, but xn is actually the random variable. So after the n product. So you can just think like this way. If you have some point, then you may have some m different choice. You can go v1, v2, v3, and also vm. But you have associated probability. But if you go someplace, then we will play the same game. So this is our first, this is our n. So the central limit theorem means if you have a random variable, then we just add until the nth step, and then we divide by square root n. And then its distribution, it converges to Gaussian distribution. So we learned it has some bell curve. So in Dolgopia's paper, actually, he left the question. So in the G, so I wrote Y is a G space, but now so in his paper, he wrote if the Y is a nilpotent, and also when the G is not compact group, can we still obtain the central limit theorem? So in this work, so now we consider Y as some homogeneous space. So we choose a lattice gamma, and then we will take the quotient. And then we will do the random walk on the fiber space. So I just want to briefly introduce what is the nilpotent group.
I'm sorry, but could you go a little before? But then, I mean, where this semi-simple condition is, may I ask you?
Where the semi-simple group?
Yeah. Yeah.
So I think that is one technical part. So I just want to briefly explain the idea of that. So in the beginning of talk, I just introduced some operator norm. If we can prove operator norm is less than 1, then we are good. But this is very difficult. We cannot check this directly. So in the case of Dolgopia, he obtained some iteration after some large iteration of operator. Then we can obtain some weaker form of contraction so he obtained such type of inequality. I mean, it should be more complicated, but just roughly speaking. So to verify this kind of condition, actually, if we have a random walk, then so I will write this one as a GW. I mean, this is just product. And then I will also consider some different walk. And then we want to find some kind of difference of these two. And then this one needs to satisfy some Diophantine condition. So in the case of semi-simple, they could obtain some models. It's not the model. I don't know how to explain, but in the sense of random walk, they define some geometric style Diophantine condition. But it is possible to define one in the case of semi-simple group. But their technology couldn't be applied in the nilpotent. Actually, I will explain why it doesn't work, because it really depends on the structure of the
Another question. So, how do you define Gaussian distribution in company group?
No. In this case, the this is the same. I mean, this is real values. I mean,
Your space is a group, right? No?
yeah, it's a
it's
group, but distribution is on R.
oh,
Yes, so it's the same.
So do you have an example of G semi-simple and Y that can be visualized? Like, can I think of, for example, G being SU2 and Y being the sphere? Or what would be like the most basic example? And
So for that part, actually, I cannot write some precise formula because his setting is quite different in this work.
so yeah. You mean Y is R, or Y is R?
This value is R. Value is in R, right? A is observable.
So Y has coordinate in R. Like G has action on Y, and
Yes.
Y has R coordinate.
No. So here, in A is observable. So if your A is in R,
No. Okay.
so the value is if you evaluate the
You
value,
use A to observe the
A
position.
is observable. Yes,
Okay.
CR of M. For the semi-simple case, if you consider sphere, yeah, as of now I cannot construct a very precise one, but I will show you how it is related. Of course, we will find some special form. So this is a just definition of nilpotent group, and we have G1 and G0, G1, and actually G1 is a whole commutator group. So this is called commutator. And we also write G of K. The same thing, but G is inside of K. F K minus 1. H is in just G. So you can see G of K is just iterating the same structure. And equivalently for the Lie algebra, we have also iteration. So we call K as a step, and step means K is the smallest number that satisfies G of K is equal to identity. And the manifold means if you have an important group, then M is a quotient by its lattice. And yeah, and also the group has a left multiplication, and also the Haar measure is given on the manifold. And here we call G as a generator of Lie group, a Lie algebra. So it means if you have a generator, then after taking some iteration of bracket, you can make all the possible elements in the Lie algebra. So here the G upper AB means abelianization. So it means if you have G sub 0, I mean G upper 0, then we will quotient by G1. So for the torus, you can write torus M in the following way. So just roughly speaking, you can think torus the manifold in this way. And we can always project to the base torus. So this one is M. And this part is G upper 0 quotient by G1. And G1 quotient by G2. And this part is G2 quotient by G3, and so on. So you can repeat this for K. But if you take abelianization, you can always have we only consider the torus on the base. So this is an example for Lie algebra. So because it is easier to it is easier to consider the Lie algebra instead of Lie group in some computation way. So a Lie algebra is called quasi-abelian. So if it has some maximal abelian subalgebra, so codimension 1. So one example is a Heisenberg. So Heisenberg Lie algebra, it has three elements in the base. The three elements, but two elements are the generators. So you can see the x bracket y. It is yes.
이것은 then your nilpotent group is compact.
Is a co-compact. No, here is co-compact. Yes.
But if it is not compact, then this torus part may not exist there, right? For example, if you just consider vector space, it is also nilpotent group, but it does not have torus part.
So in this case, we choose gamma as co-compact. So this quotient is always compact. Yeah. So we have two elements in the generator x and y, and total dimension is 3. So you can write the Heisenberg manifold as in the form of a matrix. So one generalization is a filiform. So in the previous one, we have only x and y. X, y, and the bracket gives z. But now x bracket y1 gives y2, x bracket y2 gives y3, and then so on. And then it stops at somewhere. So this is one generalization, and this part is abelian, so they commute each other. So the bracket of yi with yj is always equal to 0. So when k is equal to 2, image is a Heisenberg case. But in general case, in general manifolds for the algebra, the bracket is much more complicated. So these are just easy example. So this is a triangular, but we already know triangular matrix. So this is not interesting. So now let me introduce the setup of the work. So I will consider G is a steady nilpotent Lie group, and GI is a translation, and F is a set of generators, and we will consider some random walk. Yeah. And then we can define a operator L is from CR to CR, and then it is defined as just averaging. So here I wrote the expectation of A, and if A is observable, so here the AG is inside of A. Here G acts on Y, but in here you can view the action on the observable. So you can just see A of G composed with Y. In here it's written as X, but it has a probability. So we want to add all the multiply all the probability and then take the average. And then if you iterate this operator, then this is just conditional expectation. But if you iterate this operator, now this word comes into play. So Ln A of y or A of x is it's a P of W, and then I will write W dot x. So if you see the n iteration, then W means it will be the word from W0 to Wn minus 1. But for each case, it has a different choice from 1 to m. So we have m to the n different choice for this this iteration at the n. And then now we want to find some bound, nice bound for this operator, iteration of this operator. So this kind of operator is called Markov operator. And now the correlation function is defined in the same way. But now the difference is now L is operator, it's not T. In the previous case, we just compose the T with the A, but now we will just apply L and times. So this is the main theorem. So for any step S near manifold, so there is a constant n sub g. So what is the meaning of n sub g? So for almost every random walk generated by m, we can choose m different generators, but this number of generators should be greater than 2, and greater or equal to 2 or n sub g. So it is quite natural to choose 2 generators and then take some random walk, and then we want to prove some mixing or rapid mixing. Because if m is equal to 1, then you have only one single map. And we saw in the translation in the torus case, or S1. So if you have only translation, this is not interesting. And this is only ergodic because it never gives any mixing property. So we need at least 2 generators. But in general, in manifold, we hope to say 2 generators are enough. But in our method, we could only prove there is some lower bound, which is written as n sub g. But fortunately, if we consider some special example, like quasi-abelian, triangular, or when the step size is equal to 3, then n sub g is equal to 2 is enough. I mean, we can just choose 2 generators and then prove rapid mixing. And as a corollary, we can also obtain the central limit theorem because it's rapid mixing. So before introducing some proof, do you have any question? Yeah.
You expect that this main theorem to extend to solvable group, solvable Lie group, because nilpotent Lie group is solvable Lie group, and
Yes and no. Yeah, because yes, but in general solvable. I will show you why I said yes and no. But the main idea is Diophantine conditions. So yeah, I will explain later. Do you have any other question? So this is the idea of Diophantine condition. So I just want to briefly explain what's the meaning. So we saw the circle rotation and alpha and y alpha and so on. So let's say alpha is irrational. So if alpha is irrational, then if I start from 0 and I want to choose neighborhood, then after many iterations, it will come very close to initial point. But if some alpha is a Diophantine condition, then it means it comes close, but it doesn't come too close. So if alpha is Diophantine, then so there's some exponent, and so for any n, we satisfy such some property. So after many iteration or arbitrary iteration, it comes back to initial point, but it has some lower bound. It has some lower bound. So it cannot close, it cannot return too close. So that is a rough idea of Diophantine condition. And then we need some such Diophantine condition to prove some mixing. So in the case of the torus, I will just write our G sub j as a translation, x plus alpha j. And then we just averaging. So now we want to prove for any s, then it decays like n to the minus s. So the first step is I will consider e to the ikx because I want to use some Fourier analysis. So if you just apply this map, if you apply just this part, then you can write lambda sub k as a eigenvalue, and e to the ikx is an eigenfunction. So you can write lambda k in the following way. And when a of x has some high regularity, let's say some in CR, then we can write the Fourier coefficient decays as a k to the r. And also, if you iterate n to the n, then from the first step, we have a lambda k to the n, because lambda k is only eigenvalue. So we have just iterate. So now we want to prove some decay of the product of these two. I mean, the power of eigenvalue and Fourier coefficient. So this is this is a strategy when, I mean, this is a sum. So I want to split the sum into two parts. The one part is the Fourier mode has a high frequency, and another part is Fourier mode has a small frequency. But if the Fourier coefficient has a high frequency, then I will use the high regularity. So in this part. So if your R is large enough, then it will just decay fast. But when the Fourier mode is small, then I will apply some Diophantine condition. So this is the calculation part. So your lambda sub k is this part. But here I want to choose some lambda 1, and then I will pick up the lambda 1. I mean, I will factor out the lambda 1. And we will write the beta sub j as a difference of these two. And then the everything's are equal. So from this part, you can guess. I mean, this part is just the same thing. I just rewrote. And this part is kind of magic. But if you use some Diophantine condition, then this is strictly less than 1. So now we can hope some kind of some contraction. So this is the one key idea for the Diophantine condition, applying the Diophantine conditions. So now I will split the small part and large part. And when the frequency is small, then lambda sub k to the n is decays, like n to the minus s. And then it can be just controlled in such a way. But for the large frequency, I will just use a high regularity. So just remember the definition of rapid mixing. I mean, to prove rapid mixing given S, we just need to choose some large R. So we can just take R as large as I want. So that is the one good benefit. So here, we just need given S, we want to find the correlation decays n to the minus s. So R can be just bigger than this thing. But problem is in general manifold. How can we apply this technology to general manifold? And you see in this picture, in the general manifold, it has fibers like this. So if it is torus, then we have some random walks here. And then I chose some difference of two. And then they satisfy some Diophantine condition, it is good. But now I have some random vector in here, random vector also in here, here. Now it's a mess. I mean, you have to control every fiber level, the Diophantine condition at every fiber level. So there is one difficulty. And the idea of the word comes into play. So this is just a Diophantine condition, so I will not explain much more. And this is one technical part. But I want to just briefly explain. So just remember we have a Nil manifold like this way. And then in our work, we have omega, no, G sub omega is a product. Just n. So omega 0. And then, so these are just product, right? And each G is inside of G. But we want to control this part and this part and this part. How do we know? I mean, how do we know our product is inside of G1? Or how do we know this is inside of G2 or G3? So this is a tricky question. I mean, this is not obvious, especially if you only consider the power is positive, and 0. Then of course it's not true. I mean, just product. They may not be inside of the fiber. Okay, then what should I do? I will choose the element G and H. And I will call this is left. I will call this is right. And in the first step, I will multiply left and right. It will be GH. But in the next step, I will change the order. So it will be GH and HG. So I will call this one as my W1, and this is my W2, because they are the word. Okay, then if I take Y1, Y2 inverse, then it will be GH and HG inverse. So this is GH, G inverse, HG inverse. So this is commutator. So this is very good because this is inside of G1. So this is kind of magic, right? And then how do we find something is in G2? I will do the same thing. I will take W1, W2. I will take W2, W1. If I calculate, and this is inside of G2. This is very good. But unfortunately, it doesn't solve the problem. Why? Because I only choose G and H. I didn't consider any other thing, right? We have m different generator, and also in the product, we have many other different elements, but I didn't use. So in this kind of construction, we call the word is nice. If word is nice, then W1 and W2, they have the same length. The length means these are two words, two letters. So if I iterate this process, then they always have the same length. If I follow this calculation, like to the end. So if I can, but unfortunately, this kind of way of construction is only for very specific case. So the m-tuple Diophanty and the nice means I can repeat this process up to the k. So because these words are nice. So now I will finish quite soon. So in this construction, it's only good for m is equal to 2. And we could only verify when m is equal to 2. Yeah, we could only verify some quasi-abelian and also triangular and also step 3 case. But when m is greater than n sub g or 2, in this case, we will also use the similar type of construction, but we want to make some nice word. And then their commutation should be, I mean, it looks like commutation. I mean, or it should be commutation, but not like this way. it will be some more general. We need some more general trick to make this is inside of G1 and inside of G2. So in this case, 2 generator is not enough. So in general algebra, we found some example that n is equal to 2 cannot be proved. So before finishing, I just want to give us some idea of the Valentin's and Young's question. So this is just applying the harmonic analysis. So if you see the L to the L part, okay, let me start from the first line. If you have L to the L, then we have a sum of many different terms. And each Wj is a word, is a product. And then we need W2, W1 inverse, because this kind of form will be inside the commutator. We need to go down in the fiber level. So if I want, then I want to just split 2 terms, like W1 part and HW1. Actually, this is W2. No, this is not W2. Anyhow, I want to split this part. And then the W1 and W2 should satisfy some Diophantine conditions. But in the case of semi-simple, we don't use a commutator. Actually, they don't have a commutator relation. So in the case of semi-simple, you have some different splitting. And then they also defined some similar Diophantine conditions. So product of, but it has some kind of similar form, W2, W1 inverse. And then that kind of term should satisfy some Diophantine condition. So in our case, it is a commutator. In their case, it's not. So that is one technical part. So so this is just part of the proof. I think it's too much. So just before finishing, so yes, or if you see, yeah, so for 1, 3, I just explained. We need to consider some general nice word. That kind of construction is not enough. We need to add something more inside. And for the number 4, we also construct step 4 15-dimensional. And in general, the manifold, we believe the lower bound, the number of the element we need should be 2. But in our method, we couldn't prove it. Yeah, so I will finish that.
Let's thank the speaker for the wonderful talk. Is there any questions?
Do you think this construction of nice words would be it would be able to generalize this to general N? Like, do you think this technique of using nice words can be generalized to general N?
It is already generalized to any M. Like so, this is only for N is equal to 2. I didn't explain for general M. There's something else.
Is there like a sequence of like in between words? Like
If you have here, if you have like W1, let's say W11 and W21, but you can, if you repeat, then I want to W12, W22, and then I will repeat up to the, because the reason is the following. If you have the fiber, and then I want to stay inside of here, because every torus should satisfy some Diophantine condition. And then we need some commutation, iterated commutation. So that is the one key idea of it. But in the case of semi-simple, we don't have such thing, because we don't have a commutator in semi-simple. So he should define something something different. But the main idea is if you have a random walk, then you consider some walk W1 and some adjacent walk, and then they should satisfy some Diophantine condition to guarantee some spectra again. That is the
Is there any other questions? Okay, if not, let's thank the speaker for I want to talk.